Scientists originally defined oxidation as when a substance gains one or more atoms of oxygen. However, it can also be considered as the loss of electrons. In order for oxidation to occur and for there to be a transfer of electrons, it must happen simultaneously with reduction. This is known as a redox reaction. In this reaction, the substance that's been reduced is known as the oxidizing agent. The main difference between organic and inorganic or physical oxidation reactions is in organic chemistry, individual atoms aren't given oxidation states but oxidation levels, which are based on functional groups. If a functional group can be interconverted without the need for oxidizing or reducing agents, they remain at the same level and no oxidation or reduction has occurred.
Key examples of organic oxidation include the oxidation of primary and secondary alcohols. Primary alcohols can be oxidized into aldehydes and carboxylic acids, with the final products depending on the conditions under which the oxidation was carried out. If the primary alcohol is distilled, an aldehyde will be formed. However, if the alcohol is refluxed under allowing the aldehyde to oxidize further, a carboxylic acid will be made. This can be seen in Figure 2. In both cases, potassium dichromate should be used as an oxidizing agent. If you oxidize a secondary alcohol also using potassium dichromate as the oxidizing agent, under reflux, a ketone will be formed. This can also be seen in Figure 2. Unlike aldehydes, ketones cannot be oxidized further without breaking the carbon-carbon bonds with a stronger oxidizing agent such as potassium manganate. Due to this, a ketone, along with water, is the only product you can form by oxidizing secondary alcohols.
When a primary alcohol is oxidized to form an aldehyde, it loses the hydrogen atom that was bonded to the oxygen, and the oxygen forms a second bond with the carbon to create a double bond. This product can then be oxidized further into a carboxylic acid, and the carbon picks up another water molecule, temporarily forms a secondary alcohol, which then loses a hydrogen of one of the oxygens to make a carboxylic acid. This is an oxidation, as an oxidizing agent was required, and also the carboxylic acid is on a different oxidation level to the primary alcohol.
Ozone, or trioxygen, is a molecule O3. The generation of ozone is an oxidation reaction where a free radical of oxygen combines with an O2 molecule to create an O3 molecule. The full mechanism for this can be seen on this slide as Figure 5. First, a free radical reaction takes place to produce a single O atom with two unpaired single electrons. When this combines with O2, one electron is committed to the bond, but the other electron is then delocalized across the two bonds. This gain in an oxygen is by definition an oxidation reaction. Ozone is a strong oxidizer that is present in the atmosphere, more specifically 12 to 20 miles above the surface of the Earth. This layer plays a vital role in sustaining life on Earth by absorbing the majority of the sun's UV rays. However, man-made molecules such as CFCs are a threat to the ozone layer as they interact with the ozone molecules and break them apart by free radical substitution. Protecting ourselves from UV is not the only use for ozone. It is also a strong, widely applicable oxidizer. When it comes to reacting with CFCs, a chlorine free radical will get oxidized by the ozone to form an oxygen molecule and a ClO free radical. This reaction will continue until two ozone molecules have become free oxygen molecules, which, if this reaction occurs enough, will leave a hole in the ozone layer. Since the ozone has been reduced, it is the oxidizing agent in this reaction. Furthermore, ozone will oxidize bromide to form bromate. This is an undesirable reaction as bromate is a carcinogen.
Oxidation is commonly used in industry in things such as cleaning products, fertilizers, a process called auto-oxidation, which is used in the creation of cyclohexanol. See Figure 6. Catalytic oxidation reactions are ones such as shown in Figure 9. This shows that a catalyst is used in industry to react a carbohydrate in a certain way to get a specific intermediate for a reaction. Glucose is often a good example of this, as it is oxidized by the body into many different products. In Figure 9, this is shown in the third step when HMF is oxidized into FDCA. In cleaning, oxidation works by changing the structure of an unwanted substance. In the context of cleaning, the loss of electron typically occurs by the gain of an oxygen by the oxidized substance, and the corresponding gain of an electron from the residue by the reduction of the oxidizing agent in the detergent that loses the oxygen. In detergents, the oxidizing agents are typically compounds such as bleach or sodium hypochlorite, bleach precursors that release bleach into solution, peroxide, such as hydrogen peroxide, or peroxide precursors that release peroxide in solution. A good example of this is limonene. Limonene oxidizes other substances, oxidizes them and often puts them into their gas phase. The downside to this is that limonene is volatile and is bad to breathe in and also causes a large amount of indoor pollution. A good workabout for this would be either to not use it inside or to use a less volatile substance. Nitrogenous fertilizers are generally thought to have an important role in regulating methane oxidation, although it is believed that too much in soil is detrimental. This is because it inhibits the oxidation of methane in the soil. This is bad as methane is widely accepted to be the second biggest greenhouse gas, and soil bacteria is one of the only known natural sources of methane removal.
Despite its industrial importance, the complex mechanism of cyclohexane autooxidation by O2 is still largely unknown. The autooxidation of cyclohexane has been of interest for many years, and one of the few things that we know is that oxidation is known to proceed through a radical chain mechanism. The oxidation produces cyclohexanol and cyclohexanone, also known as Ka oil, among other byproducts. Because the primary products are more reactive towards oxidation, the industrial process is carried out at low temperature and pressure, where cyclohexyl hyperoxide, cyclohexanone, and cyclohexanol are all the major products. Catalytic oxidation of carbohydrates and carbohydrate-derived molecules include important acids such as formic acid, acetic acid, and glycolic acid. Formic acid has an annual production of 720,000 tons per year, so it's a much-needed resource in industry and is mainly used as a preservative and antibacterial agent in livestock feed. It can also be used in the production of leather for tanning, dye, and its finishing. It can also be found to be in place of mineral acids with various cleaning products such as limestone remover and toilet bowl cleaners. It can also be used in organic syntheses as a source of formal groups and a source for hydrogen proton transfer and hydrogenation reactions. Organic oxidations are numerous and has a large outreach. Everything from the generation and depletion of the ozone layer to the industries and jobs it supports within the chemical and livestock fields. The simple definition that all oxidation is the loss of electrons. There's so many different uses and implications, and a small amount of them have been discussed here, and even then only the surface was barely scratched in this presentation. So many topics and ideas within organic oxidation, it would be impossible to discuss them all in one go.